Test. Okay, so my name is Alexey Harlamov. I work for a company called IPAM Systems. And first of all, I would like to thank you for coming here today. It's been a long day, and I hope I won't wake you up too much. But but you have to promise me that if I will start to fall asleep, you will wake me up. My local time is around midnight. So today I wanted to talk about post-trade processing using in-memory data grids. This presentation is based on one of projects I've been through during my career, though it's a little bit outdated. It's have been moved to production 5 years ago. So who is in the room knows how trades are processed, right? How does trade processing look like? So, okay. Don't be too hard on me. I'm not expert. So, if you think about it, at the surface, this looks fairly simple. Two agents decide to buy or sell some assets. One guy wants to sell 1,000 shares of Apple, another one wants to buy, and they come to a single place, a market. And usually they are not doing it directly. They go to an entity called broker, which puts this order into a matching engine. And by matching engine, sorry, could you decrease volume of the monitor because brokers put these orders onto a matching engine. And it can be just a phone call network. One broker can call another one and ask, do you want to buy it? All in all, they come to an agreement, a deal. And this deal is sent to a clearinghouse, which actually guarantees actual execution of this deal. And he takes this captured trade and coordinates settlement, transfer of actual assets from one place, depository, to another place, and cash in the reverse direction. However, some companies, they play all three roles. They are brokers, they are clearing members of the market, and they are depositories at the same time. And if you think about business of these entities, global clearing members, they like to provide their clients access to as many markets as possible. And there are a lot of them. There are more than 100 exchanges or markets, whatever you call it. Those provide access to very different asset classes. Swaps, bonds, equities, derivatives. And this distribution across the globe, right? All these markets, they are located in different places. United Kingdom, New York, Chicago, Singapore, Australia. They are in different places. So your data processing infrastructure, your trade processing infrastructure is distributed across these locations as well. For example, order management, where you put your orders, are going to be close to exchange. Your accounts, account management system, and risk exposure going to be close to your client. Booking can be in a very different place. And you need to do around-the-clock operations, which means you run this trade clearing almost 24/7, probably except 6 hours time window from Saturday to Sunday. To make things interesting, if a clearing member of market is not functioning for a day, and this is well known among these guys, they actually going into default state. They are out of business. They are bankrupt. So you cannot allow your system to be offline for 24 hours. Together with that, you need to design to facilitate addition of new markets, because they appear and change their rules pretty frequently, and you need to change your system together with them. So this is business restrictions. There are a few technical ones. There are multiple parties involved in the process of clearing trade or post-trade processing. As I mentioned, brokers, exchanges, depositories, and you need to coordinate across of them. In a perfect world, you can do a global transaction, right? You can do it as an atomic operation. In addition, you have multiple internal systems, because these global brokers, they grow by acquiring small local companies, or comparatively small companies. So you have systems spread across these companies. Different asset classes, they can be processed immediately in real time, or there can be 3 days window which allows you to do whatever you want with this transaction. So basically your result is delivered 3 days after the trade was made. These factors, they significantly multiply your write workload. And if you look at trade capture data feed, it's probably tens of thousands of trades coming to the system per second, at tops, right? But take into account that you need to do processing in all these different systems inside your organization and outside of your organization. You probably can multiply it 12, 20 times. So instead of 10,000 messages coming into your system, you will absorb like 200,000 updates hitting your system. And to make things even more fun, a broker frequently does complex things with captured trade. So when they put order onto a market, they might have aggregated multiple orders. So when you receive some assets, you want to allocate them to your accounts. So effectively, you split your trade into multiple separate processes. Those are relatively independent. And this leads us to a very interesting situation when we need to process transactions across multiple geographical regions and do a lot of such operations. As I said before, in a perfect world, you can do XA distributed transaction, you're good, but usually your internal systems and external system won't support it. So you actually have only one fallback. You have to return to state automaton-based processing when you know how the transaction is going through all these steps, and if something goes wrong, issue reversal messages. You basically cannot roll back changes in external systems. You can only issue a reversal, an version of your operations. So I was said some time ago that ACID is designed and going always be in financial industry. And this is the only thing which is acceptable for financial industry. But if you think about it, this is a perfect example of base paradigm in banking, in trade, because you provide basically available system with soft state, and which is eventually consistent. You probably achieve consistency by end of transaction or trade clearing time span. And specifically for this transaction, you never achieve a consistent state in the system. So how you design such system, which is large, and if you think about it, whatever mistake a human can do, it is going to be done. And we actually had a situation when production system was broken by a release engineer who was updating QAT and just restarted production. So what you design is for recoverability, or you actually design with failure in mind. And ultimate way to recover things is actually redo them. If you're writing an essay about some topic and then you are not happy with the result, what you actually can easily do is drop results of your work and then start from the very beginning. And this is the whole concept, which is very widespread in financial industry. You basically try to take the input data and replay and redo your processing. And in order to do that, you need to make all operations in your system idempotent. So you cannot charge an account twice for specific trade. Another step is failure domain isolation. And by that, I mean, if you are breaking some piece of the system, these issues, these failures should not propagate through the whole system. So you isolate aspects of your system. You isolate change. Change in interface are not going to be propagated to other parts of the system, and it should be concentrated in a specific place. Then you try not to put your code describing business logic into your data grid, because a restart of a data grid is an expensive and a little bit risky procedure. And if somebody who was developing this code made a mistake, like causing memory leak, you will bring down the whole system. So you want to minimize number of such events. Plus, you try to change your system in a way that code changes do not impact data storage format. Specifically for this project, we used fix, we used text, we used JSON. We tried to avoid non-portable data formats. Plus, standard for financial services, traceability, or all operations, all changes in all accounts actually recorded as a separate entity and stored for subsequent triage or troubleshooting. And it's pretty frequently used no single point of failure design when you try to avoid any components in the system. Those can bring down the whole system. So if you have a single server which will break your system, sooner or later it will happen. Specifically, this system, it had 130 servers working together. And if one of them could break the system, it will happen. Plus, in financial world, you usually plan for single data center failure. I've never seen this happening, but nonetheless. So, when we started the project, we had a joke about message router from hell. Basically, we had 200 endpoints talking with each other in fairly random fashion. So the company grew organically, and they were building code, day to day. And there was no order in this structure. It was almost a fully connected mesh. Business logic was implemented inside endpoint services. And if something was going wrong, there was no way to quickly identify which part of the code was broken. At that point, we came up with the idea of domain-specific language to describe business process. And if you think about it, this is a very good paradigm to describe business process, and there are plenty of engines that allow you to do that. But at the same time, this system and similar systems are quite unique in terms of performance. So we came up with very similar design. When you have a text description of your business process, which hides all complexities of distributed system, like replication, reordering, failure recovery, and business logic developers were able to work on it separately from people who were taking care about the platform, the processing platform. And we were capable to use standard tools like static code analysis, version control systems, merging, diffs, continuous integration, continuous delivery for these processes. And if you think about it, it is simple Java code which explains your business process. And that can be easily broken down into pieces synchronously executing and asynchronously executed on the grid. This process was a sequence of steps or actions. Those can involve transformation of data plus communication with the external system, which was always done through a queue. So this is generally the high-level architecture. An exchange is talking to adapter or connector, which in turn sends data to a feed repository. Feed repository's only goal is capture the incoming data feeds. And then behind this highly available feed repository, you have a system which we call processing grid, which contains state of all business process or all trades happening in the system. And it was talking to external world through adapters, plus some persistent back storage to support that. Why do we need a feed repository? It's fairly well-known concept, and it has several functions. It captures inbound data feed. So if something goes wrong and operations team wants to reprocess specific transaction, it goes to feed repository and says, please resend this trade capture event for processing. You basically can restart processing of specific trade. Or you can go there and say, the whole processing grid is down. We need to reinitialize it. Please send all data for the day. Plus, there is side function of sending data to a test system. Another function is message buffering. It allows you to safely restart processing grid. Basically, you shut down the processing, brings it up, no data is lost. And you have a authoritative source of information. If there is a problem or argument with Exchange, you have captured your raw input data. You have a proof it was your mistake, their mistake. And this functionality, it's usually provided by exchanges, but it's not very convenient for a company to request information from Exchange directly, because it's basically admitting we screwed up. In terms of technical design, what we basically did, we created in-memory data grid, which was split between two availability zones. And all data from one availability zone were replicated to another availability zone synchronously. Every write to feed repository was a write to persistent storage in availability, primary availability zone, secondary availability zone, memory of the data grid, and that allowed us, that allowed us to be resilient in face of single data center failure. Because if you have your data copy in both data centers, one of them goes down, you are still online. So now to processing data grid. And it's simply a partitioned distributed cache which contained state of trades. So we had partitioned region called state, describing processes, with replication factor 2, which means there was always a copy of data on another node, and single node failure was not causing any issue. And we also maintained dictionaries or reference data there, plus description of processes. So if there was any change in state of a process or state of the trade, we had an update listener which was basically expecting something to change with the process and then progress it according to the original description. That company, it had locations or operations in 3 regions, basically Europe, United States, and Asia. So they had operations team in all 3 locations. And we replicated data to all these locations as well. So if London operations team ends its day and goes home, guys in Singapore can actually continue to work on clearing the trades, even from London Stock Exchange. And obviously, you would like to have a synchronous replication here, but with round-trip times, it's not possible. Singapore to New York, no, to London is around 200 millisecond round-trip time, which means your write operations, if you're using synchronous replication, is going to take 200 milliseconds, right? And it's basically non-viable from performance perspective. So we had to go with a synchronous replication between data centers. Those were roughly in sync because of that. So how did processing actually work? Data grid, processing data grid was forming messages to external systems. And for each external system, we had a group of adapters. Very simple process, web applications actually. Those taking data from a queue, doing some transformation and sending data to external system, clearing system, account system. Basically, adapters were embedding protocol specifics. Some systems, they use messages, some systems are integrated using stored procedure invocations. And these adapters, they have to be, first of all, resilient to failure of one node. And Secondly, it has to be horizontally scalable because some of the interfaces are fairly slow, which means you need to have multiple of them. And it introduces message ordering problems. So if you have a single queue and single consumer, this consumer extracts messages from the queue in order. If it fails, messages returned to the queue, everything is fine. But if you have multiple of them, they take data or messages from the queue in chunks. And if one of them fails, a chunk can be returned to the queue. That means some of the adapters can process messages out of order. You actually can observe a situation when, update for the record comes in after delete has been processed for the record. And when we started this thing, assumption was there are going to be very, very small amount of messages of such kind. Reordering is not an issue. But actually, what we observed in the distributed setting is 3% of our messages were coming out of order. So we had to resolve this problem somehow. First thing you realize is that trades are processed in parallel. So, and it's oversimplification, of course, but what you can achieve is partial ordering, ordering of messages specific for a trade. So we come up with this idea that each command to an adapter also contains a predicate, which checks that state object is in the right state. And for most of the cases, it's going to be state object is having sequence X, right? Then when you get this command, you evaluate the predicate. If it's true, you continue. If it's false, you place your command into a holding tank. And this holding tank, it's just another region collocated with your state region. When update comes in for a state, it basically requeues this command for evaluation. Another thing which we had to go with is update command queue for states. If you think about it, you can have adapters across multiple locations, and they can work in parallel. So they can try to update state at the same time. And it's very hard to resolve because it's actually distributed operation. So for each of the trade, we assigned a home location, a data center which was executing updates for specific trade, for specific state. That means wherever you want to change the state, you issue a command, and this command is replicated to every location. But only one selected state, selected data center process update for it, and actually changes the state object. Cross-site replication. Again, round-the-clock operations. Singapore continues work of London. United States pick up work not finished by Singapore. So you need to have a global view across all these locations. So we had 6 data centers in fully connected mesh topology, which were replicating data between each other. And I think it's not very interesting aspect, but nonetheless, what we observed is that replication across a single TCP connection is imposing an issue. If you have a dedicated channel between Singapore and London with round trip time of 200 milliseconds, you have a limit on a throughput of TCP channel based on size of your TCP window. And that means you need to create multiple TCP connections between these data centers and do replication in parallel. Plus, it turned out the technology we used for the matter did not have toolkits for operations like data center synchronization. So frequently when you have an issue, you want to resynchronize sites A and B. And for some reason it was not available. Persistent store. We had a lot of argument if we need that kind of functionality in the system. So obviously we need to archive data coming into the data grid and remove outdated records, or for archival purposes and for analysis for reporting. So we had simple Oracle database in each of the data centers, which was pulling data from the grid. But at the end, we decided to use persistent store for the data grid as well, basically to accelerate recovery after reboot of processing grid. And this happens especially during initial development quite frequently, when you need to modify code hosted inside the grid. If you would need to reprocess all input feeds, it would take maybe a few hours. This persistent store allows you to restart processing grid faster. Nonetheless, we had quite a few issues and deadlocks in this system because it's really hard to implement. And by the end of the day, we were using scripts that will bring it up the system in specific order. So all cluster members were starting in specific order, just to avoid deadlocks. So, just to summarize, domain-specific language to describe process, synchronous and easy to reason about, centralized process description, minimum custom code inside the grid, just to avoid restarts of the system, and ensure that all updates are actually having traces recorded somewhere. That's it. I'm ready to answer questions. Thank you. Any questions? Okay, thank you.